Assalamu alaikum. In this lecture we are going to study the characteristics of the directional relays. As we discussed earlier that in overcurrent relay we only require the magnitude of fault current in order to detect the fault. But in case of a directional relays we actually require the power flow value. So for the calculation of power we require two different quantities. One is current and the other one is voltage. So therefore we require CT as well as PT in order to operate the directional relays. The voltage that we are getting from the potential transformer is VPC, and the current that we are getting from the current transformer is ICC. So there is a current coil as well as a potential coil in the directional relay. So if you remember from the overcurrent disk type relay, the mechanical relay that we discussed in detail previously, there is the requirement of two different type of fluxes, phi 1 and phi 2, and they should be having an angle of theta between them in order to produce some torque. So there should be two different fluxes in order to produce torque which are displaced by an angle theta. So in this case we have one flux from the voltage value that is coming from the potential transformer, and the other flux is being generated by the current coil current that is actually the fault current in case of any fault occurring. So in this case we can easily calculate phi 1 and phi 2, which will be actually phi cc, the flux that is due to the current that is passing through the current coil, and the other one is phi pc, that is due to the voltage that is being applied to the potential coil. And in this case we require a polarizing quantity for the fault detection, and the polarizing quantity is the one which do not change its value or its direction when there is a forward or reverse fault. So in both the cases this polarizing quantity should remain same or its direction should not change in terms of phases. So in this case the VPC value, the voltage of the potential coil, will remain same, but in the case of forward and reverse fault the direction of current will be changing. So therefore the polarizing quantity in this case will be VPC, the voltage that is being applied to the potential coil. And once these two fluxes will produce some sort of torque, then there will be a signal that will be sent to the trip contacts, and this trip contact will either send a signal to the overcurrent relay to check whether there is a fault or the fault value is above the minimum fault current value or not. If the overcurrent relay also finds that there is the fault in the system, then it will trip the circuit breakers. So this is the basic working principle of the directional relay. So in order to check the directionality of the fault, we have to draw the phasors, and we will talk about these phases in the coming slides. This is the basic phasor diagram that is usually made for the directional relays in order to check whether there is a fault in the zone of the directional relay or not. So first thing to remember is this voltage VPC is taken as a reference, which is a polarizing quantity. And this VPC is applied across the potential coil, and if there is a potential coil then the current that is passing through the coil A will be having an angle closer to 90 degree. So therefore the current IPC is lagging the VPC, which is the polarizing voltage, right? So as the coil is an inductor, so if there is an inductor, the voltage and current will have an angle closer to 90 degree, and the current will be lagging the voltage that is applied to the potential coil. Similarly, there will be a current that is coming from the CT, and with reference to the VPC value, this current will be leading the polarizing quantity or VPC or the voltage that is coming from the potential transformer. Now there is an imaginary line that is actually defining the maximum torque line, or defining the current ICC which will be producing the maximum torque in the relay, and this ICC will be at an angle tau from the polarizing quantity, which is VPC. The angle between VPC and IPC is theta PC. The angle between the VPC and ICC, the current coil value of current, the fault current ICC that is being measured by the CT is theta, right? So we have to define two different regions by using this particular phasor diagram. One is the restraint region, which is actually defining the reverse fault region. The other one is the trip region, which is this one. So this is defining the forward fault region, which is within the zone of the directional relay, right? So this is the basic characteristic diagram of the directional relay, or you can also call it the phasor diagram of the directional relay. Now the basic formula for the torque that we calculated earlier is this one, phi 1 phi 2 sine theta. Here these two fluxes are separated by an angle theta, and if you have to calculate the maximum torque value, then this sine value should be maximum, and in order to make this sine value maximum, we have to make this theta equal to 90 degree. So sine 90 is equal to 1, so there will be a maximum torque when the angle between phi 1 and phi 2 is equal to 90 degree, right? So in this case we have two fluxes. One is being generated by this ICC. So let me just clear this one a little bit. So we have two fluxes. One is due to ICC, which is from the current coil, and the other one is due to IPC, that is passing through the potential coil, which is phi PC. So in this case we have an angle theta between phi 1 and phi 2. Now we have two different fluxes. One is phi CC and the other one is phi PC, and the angle between these two fluxes is theta plus theta PC. So there is sine here, and torque is directly proportional to this value. Now in order to make this tau maximum, we have to make this sine value equal to 1, and in order to make this equal to 1, we have to make theta plus theta PC equal to 90 degree, right? So that's why this tau line, this particular maximum torque angle line, is at this particular orientation, and the angle between these two fluxes phi CC and phi PC is tau plus theta PC, which is equal to 90 degree, right? So this theta is equal to 90 degree minus theta PC. So that's why we have a line here that is making actually the angle tau, and the summation of this tau and theta PC is equal to 90 degree. This is the formula that I was talking about. The T operating value is phi PC phi CC sine theta plus theta PC, and theta plus theta PC is here because this is the angle between these two fluxes, Similarly, in order to make this torque value maximum, we have to make this value theta plus theta PC is equal to 90 degree. And from the phasor diagram, we know that theta PC plus tau is equal to 90 degree, and theta PC is equal to 90 degree minus tau. And putting this value here, theta plus 90 degree minus tau is equal to theta minus tau plus 90 degree. And converting this sine into cosine by using this 90, we have cosine theta minus tau. So operating torque is equal to K1 times phi PC, which is the flux through the potential coil, and the flux due to the current coil is phi cc cos theta minus tau. And we can replace phi PC with VPC and phi cc with ICC, right, because they are proportional. And when we'll replace these two values here in this formula, then this K1 constant will be converted into K2. So this will be the formula that will be used for the directional relay operating torque calculation. And here from the phasor diagram from the previous value here, the tau is actually equal to 90 degree minus theta PC. So this is tau, this is theta PC, this whole angle is equal to 90, so tau plus theta PC is equal to 90 degree, so tau is equal to 90 minus theta PC. Now we also know that the pressure coil is highly inductive because it is a coil, so its inductance is high. So if its inductance is high, then the voltage and current angle will be closer to the 90 degree, which is approximately equal to 70 to 80 degree, and the current is lagging the voltage. In case of inductor, right? So that's why theta PC is between 70 to 80 degree. So if theta PC is 70 to 80 degree, then tau is actually 10 to 20 degree. So in the previous diagram here, the tau will be approximately equal to 10 to 20 degree, and the theta PC will be approximately equal to 70 to 80 degree values, right? So now the question arises is that how can we define this zero torque line? On one side of the zero torque line, we have a restraint region, and on the other side we have a trip region. Now we want to make this operating torque maximum, and in order to make this operating torque maximum, we have to make this whole term maximum, right? And for that, cosine theta minus tau should be equal to 1, right? And cosine is positive in first and fourth quadrant, right? So this theta minus tau should be within this range. From minus 90 to 90 degree, we have a cosine value which is positive, so we have a maximum operating torque value. And from there we can write minus 90 degree plus tau and 90 degree minus tau, sorry, plus tau. So if there is no tau in this inequality, then this will be your zero torque line. But now we have to add tau in minus 90 degree as well as in 90 degree. So this zero torque line, if there is no tau, will be tilted by an angle tau, so which is this angle and this angle. So these two angles will be equal to tau. So that's why this zero torque line is tilted by an angle tau. We have to make this cosine maximum and positive, so the cosine value is positive in first and fourth quadrant, so that's why we have a tilted zero torque line. And we have two quadrants, which are first quadrant and fourth quadrant. So this is your fourth quadrant and this is your first quadrant. So these are the two regions in which we have a positive torque and the maximum torque. So if there is a fault current that is in this direction on the right side of the zero torque line, then the relay will trip. Otherwise, if we have current in any of these directions, the relay will restrain and it will not consider that fault in its own zone. So this was explanation of zero torque line. Now there is another point, that when we were considering the current through the potential coil, it was considered to be lagging. But when we considered the current through the current coil, it was in the leading scenario. But both are the coils. So if in both the cases we have coils, then ICC should be in this direction as well. But the phasor shows that the ICC is leading VPC, right? So why is it so? Whenever we have a line, for example, this is a transmission line, and we have a circuit breaker here, we have a directional relay that is attached to this one. This is your directional relay, and this directional relay will have some current value from CT as well as the potential value voltage V from the potential transformer. So whenever we have a fault at this point, there will be some VPC value that is sufficient for the operation of the directional relay. But as this fault is moving towards the relay point, or the point where the relay is attached to the system, the VPC value will start decreasing, and very close to the relay point, or the point where the relay is attached to the system, the VPC value that you are getting from the potential transformer will be so less that it will not be able to help out in the decision making. So this value will be very small. So if this value is small and you are not able to make the decision based on this VPC, then we should use some other polarizing quantity that is not affected by the fault occurrence. For example, we have a fault in phase A, then the voltage VA will be affected by the fault in phase A, but the other two phases VB and VC, they are not affected. So we can use the line to line voltage VBC in this case, right? And line to line voltage, we know that VA, VB and VC, all these voltages have an angle of 120 degree. Now if I have to calculate the line to line voltage VBC, so this will be your VB and this will be your minus VC, and this phasor will be representing VBC, right? So if we take this VBC as a polarizing quantity, which is VPC, then the current that is related to VPC is IPC. This will be in this direction, this is your IPC, and the fault current will be with respect to this VA, which will be somewhere here closer to 90 degree, right? ICC. So if I rotate this phasor, it will be something like that: VBC, ICC and IPC. So this is your potential coil current, this is your polarizing quantity which is equal to VPC, and this is your IC, that is the fault current in this case. So that's why in this phasor diagram the ICC is leading the potential coil voltage, because we are considering line to line voltage here, and this ICC is lagging with respect to the phase voltage in which we have a fault. For example, in this case, if I am considering we have a fault in phase A, the current IA is with respect to VA, the voltage of phase A. But in case of fault in phase A, we will be considering the voltage VBC as a polarizing quantity. And with respect to this VBC, the potential coil current will be lagging and will be in this direction. Right? So that's why we have a coil current leading the potential coil voltage and the potential coil current lagging the VPC, the polarizing quantity. So these are the basics of the phases that are drawn for the checking of directionality whenever we are applying the directional relay. So these are the basic characteristics of the directional relay. Thank you.